Hello, everybody. Here we are, 4.2 integral exponents. Yes, integral, not integral. So not the kind of most important or essential, but related to integers. So an integer, as you recall, are kind of like our positive and negative. Can't I write very well? Negative counting numbers. Or like whole numbers, though whole numbers are positive integers. So, 1, 2, 3, 4, 5, but also -1, -2, -3, -4, -5. And we are kind of like most concerned, I would say, in this lesson with the negative one. So what do we do when we have a negative exponent? So let's go over some of the laws. I know we've done this before, but they all apply in the same way, and so it's really important to remember them all. The product of the powers means that if we have the same base, so we have a to the m times a to the n, it's the same as a to the power of m plus n. So if we have, 2 squared times 2 squared, that's 2 to the power of 2 plus 2, so 2 to the power of 4, or 16. For the quotient of powers, this states that if we have a to the power of m divided by a to the power of n, so the same base, this is equal to a to the power of m minus n. So if we have, 3 to the power of 3 divided by 3 to the power of 2, this is the same as 3 to the power of 3 minus 2, 3 to the power of 1, or 3. Power of a power states that if we have a to the power of m to the power of n, it's the same as a to the power of m times n. So if we have, 2 squared and that's cubed, you can multiply the exponents. So that's the same as 2 to the power of 6, because this is saying you have 2 squared 3 times. So you have a 2 squared and a 2 squared and a 2 squared, means you have 2 to the power of 6, and that's, what is that, 32, I think 64? Let's see. 2 to the power 6. There we go. The power of a product means that if we have, a times b to the power of m, that's the same as a to the power of m times b to the power of m. So this is kind of, I think, more useful when you have letters. I mean, sometimes you might solve inside the brackets first. Sometimes you do, sometimes you don't. So if you have, say, for example, I'll show it with numbers though, 3 times 4 squared, that's the same as 3 to the power of 2 times 4 to the power of 2. So you can distribute the outside exponent inside. And similarly, the same for power of a quotient. Let me scroll. That if we have a over b to the power of m, that's the same as a to the m over b to the m. So if we have, 2 over 3 to the power of 3, it's the same as 2 cubed over 3 cubed. And the zero exponent law is that if you have, a to the power of 0 and a doesn't equal 0 itself, that a equals 1. So anything to the power of 0 equals 1. So 5 to the power of 0 equals 1. -5 to the power of 0 equals 1. X to the power of 0 equals 1. And here we are, negative exponent, that if you have, a to the negative m is the same as 1 over a to the positive m. And it's also true that if you have 1 over a to the negative m, it's the same as a to the positive m. So basically, I would also like you to write down that it reciprocates reciprocates the base. So you notice here that we kind of previously had an a over 1, but now we have a 1 over a. Here we had a 1 over a, and now we have an a over 1. So it reciprocates the base. So, I'm going to say, for example, we got 3 to the negative 2. It's the same as 1 over 3 to the positive 2. Also, if we have 1 over 3 to the negative 3, it reciprocates the base, so we can change that. We can flip our base, and it becomes 3 over 1, or just 3 to the positive 3 to the positive 3. And I want to show you why this works. I have this number line here to demonstrate, and I have a kind of another way to show why this is. So let's call this, 1 or 2 to the 0. And then, so if we have 1, here's, 0 right here, let's say. If we have 1, and our next step is going to be 2 to the 1, so our, if we're going 2 to the 0, 2 to the 1, we would double this section right here. So we've got 1, and now let's double it. So we're going to end up going another section like that. We just doubled that. That's what the base means. That's what, our base 2 means, that we're doubling each time. So now we're at 2 to the power of 1, or 2. And now for our 2 to the power of 2, this section here that we have, these two spaces, we're going to double that space again. So now we double that, and we've got 2 to the power of 2, or 4. And now to go to 2 to the power of 3, let's double that. So double all of this. We're going to end up with 5, 6, 7, 8, 2 to the power 3. So let's double all of that. And there we go. And now we're at 8. We could go again. I think we have enough space. 9, 10, 11, 12, 13, 14, 15, 16. 2 to the power of 4. So we're going to double all of this. So let's double it. And we're at 2 to the power of 4. And that whole thing is 16. So now what happens if we kind of we have 1 right here? What happens if we undouble that? What happens if we have the opposite of doubling this? I would say that we half that. So we end up right here. Half of 1, we're going to bring it to a half. So 2 to the power of negative 1 is going to land us right here. 2 to the power of negative 1 is going to land us at 1 over 2. So a half. And 2 to the power, now if we half that half, we end up just a little bit further. We're going to end up right here. 2 to the power of negative 2. We're going to land right here at a quarter. 1 over, 2 to the power of 2, or 1 over 4. So that's why it works. And I want to point out as well that these have a reciprocal relationship. So that 2 to the negative 1 and 2 to the 1. So we have 2. You think about that as 2 over 1. And its opposite is 1 half. So the flip of that, the reverse of that. Here, 1 over 4. So 2 to the negative 2 has a relationship with 2 over 2. So this is 4, this is 1 over 4. So it reciprocates that. And here's another way I want you to think about it. One way that I want to show you that it works using exponent laws. So say we had x to the 3 divided by x to the 6. And if we know that means that we can have x to the power of 3 minus 6, we're going to end up with x to the negative 3. And if we drew this out, here's what this looks like. X to the 3 looks like x times x times x. And x to the 6 looks like x times x times x times x times x times x. And if we cancel out all of our x's, we're left with these 3 on the bottom. So it's going to look like 1 over x to the 3. So this becomes this. So those I think are my best ways of understanding why this works or demonstrating why this works. And now let's do some examples together, and hopefully that'll help you out. So here we have c to the power of negative 4, which equals 1 over c to the 4. On B, let me give myself some more space, or no, that's okay. I might want to save this actually. Oh, I want to save this for my key behind the scenes. There you go. This means that this reciprocates our base. Our base is currently 2 over 3, and now we reciprocate it, so we flip it. This is equal to 3 over 2 to the positive 2. And we can solve that further by distributing inside. So we can distribute this 2 to the 3 and to the 2 down there. So we get 3 squared over 2 squared. That equals 9 over 4. And I think we could leave it like that. We can put it as an improper or a mixed fraction. I'm going to leave it as 9 over 4. Let's do our next one. And it's important to note that this negative only affects this. Our base is actually the x, not the 3x. So it's only going to affect the x. So we're only going to move the x to the bottom. So we end up with 3 over x to the 3. And maybe I should show you a step kind of before that. If we want to split this up, this is essentially 3 times x to the negative 3. So we can move this to, end up being 3 times 1 over x to the positive 3. And this is like a 3 over 1. And now if we multiply these two fractions, 3 times 1 is 3. 1 times x to the 3 is just x to the 3. But, so we can think about it like that. That's the steps, but this is how it moves. Again, here we have just one negative exponent. It only affects this n. So we can keep our positive 4m to the 3 on the top and move our n squared to the bottom. And if you wanted me to show what that looks like, it would be 4 over 1 times, m over 3 to the 1 times 1 over n squared. Then we can multiply the tops. We get 4m cubed over n squared. Okay, let's do a few more. Here, remember, it's only affecting, if this were in brackets, we had negative 2x to the negative 4, then it affects everything inside of it. Because it doesn't have the brackets, it only affects the base right there. So here's like we have negative 2 over 1 times 1 over x to the 4, and that equals a negative 2 over x to the 4. And here we go. We have a negative exponent on the x and a negative exponent on the y. So you can think about this as negative 5 over 1 times 1 over x to the 3 times 1 over y to the 2. And now that ends up looking like negative 5 over x cubed y squared. Okay, let's solve these ones, and let's use our exponent laws that I went over at the top. So here we have the same base. They're being multiplied, so we can add the exponents. We got 2 to the power of negative 2 plus 3. Remember, a negative 2 plus 3 is going to give us 2 to the positive 1. And if you wanted to show kind of why this works, I'll show what we've got going on. We can reciprocate that and make it as 1 over. Okay, got cut off by my 15-minute limit, and I'm coming back much later. I think I got to here, and I'm showing you why this works. So if you have 2 to the negative 2, it's like 1 over 2 squared, so 2 times 2. And this whole thing is times 2 to the 3, which is 2 times 2 times 2. And you can consider that over 1. And if we multiply those together, we get 2 times 2 times 2 over 2 times 2. And you can reduce those just become 1s, and you're left with 1, 2, or 2 to the 1. So that's maybe a kind of visual of that, if that's helpful. Let's try the next one. We have, and I don't know if I pointed out, but we are just simplifying. And they want us to state the answer using positive exponents. We don't need to evaluate. We don't need to make it into standard form, but we do need to show in a kind of simplified version with positive exponents. So we have base 3. We have 0 minus negative 3, or sorry, plus negative 3, because it's multiplying. And so we get 3 to the negative 3, which equals 1 over 3 to the 3. If we were evaluating, that'd be 1 over 27. The next one, we have the same base, and it's being divided. So now is when we minus. So we go 5 to the 3 minus negative 4. So if you recall, when we minus a negative number, it's like adding a positive. And so we have 5 to the 3 plus 4, so 5 to the 7. Next one, let's deal. We can deal with we need the same base for the rules to apply. So we can do the 3s and we can do the 4s. So let's deal with the 3s. We have they're being divided, so we have to subtract them. We have 3 to the negative 7 subtract 9. Let me just 3 to the negative 7 subtract 9. That's going to leave us with 3 to the 16, a negative 16. Let me just write that a little better. Negative 16. And the 4 is going to be 4 to the 1 minus 3. It's going to leave us with a 4 to the negative 2. So we end up with the 3 to the negative 16 and a 4 to the negative 2. Since they're both negative, we can put them both over 1. And 3 to the 16, 4 squared. We'll just leave it like that. It's just asking us to simplify, not evaluate, so we just leave it that way. The next one doesn't have any negative exponents. I'm not sure about this example, but why not? We can just distribute this 3 inside, because essentially what we're saying is we have 2 to the 4 cubed, 2 to the 4, 2 to the 4. And now we have the same base being multiplied. We could add up those 4s. We get 2 to the 12, which would have been the same if we had just multiplied the 3 by the 4 in the first place. Next, we can do the same. We have a negative 4. We can multiply that inside. So we get 3. 2 times negative 4 gives us a negative 8. And now we can flip the base, and we get 1 over 3 to the 8. The next two, there's kind of 2 ways to approach it. As long as what you're doing is mathematically correct, I think you're going to get to the same place. But if we want to stick to kind of like BEDMAS laws, you can deal with what's inside the brackets first. But I'll show you both ways. So in this one, I'm going to deal with the inside first, and then we'll deal with the negative exponent at the end. So we have 4, and then we have a 2 to the negative 3. So we can think about this as 4 over 1 times 1 over 2 to the positive 3, which would give us 4 over 2 to the positive 3. And this whole thing is still to the negative 2. And now when we have a negative exponent, we can flip or have the reciprocal of our base. So we have 2 to the 3 over 4, and that's to a positive 2 now. We flipped our base, and now we can distribute the 2 inside to each of the exponents. Remember, there's an invisible 1 right there. So now we get 2 to the 6 over 4 to the 2. And I mean, you could maybe reduce this further. I think this is a fine final answer. You could change this 4 into a base 2, so 2 to the power of 2. But I'd say this is an acceptable answer for what the question has asked us. And the last one I'll show you, you could also just start with distributing the negative 3 inside and then deal with the bracket after that. We get negative 3, so that's 6 to the power of 2 times negative 3, so to the power of negative 6 over, we have 5 to the power of negative 3. Negative 3 times the negative 3 is a positive 9. And now our 5 to the power of 9 is positive. It's going to stay where it is. But the 6 to the power of 6, we can bring it to the bottom. So now we have 1 over 5 to the 9 times 6 to the 6. There you go. Thank you so much. I'll let you know what textbook questions I'd like you to do.